Newton's second law of motion. So when you do this section or when you get into this, and guys, this video you're in for the long haul, right? So I've done every type of example that you could get, every type of scenario. So as you work through the video, you will see that there's friction questions, non-friction questions, but a foolproof method on how to get through each of these questions, right? So don't stress about it. Watch the video. Make sure you take notes. Take down the questions. Take down the free body diagrams. Draw diagrams. Make sure you do the calculations. See how these systems work. Don't just blindly watch the video without engaging with it. I pause the video sometimes, see if you can do the calculation by yourself, watch the solution. You may learn something new. You also may learn something for the first time. So please make sure you have a look. Now, the first thing that you need to be able to do is state the law. When a net force is applied to an object of mass m, it accelerates in the direction of the net force. The acceleration a is directly proportional to the net force and inversely proportional to the mass. That definition, you must know it off by heart, word for word, so there's no negotiation with that. That gives rise to the formula F is equal to ma, which we're going to look at now. Variety of equilibrium and non-equilibrium problems. Now, with equilibrium problems, we've dealt with some of that, but the non-equilibrium ones are the biggest situation that we have here. And we're going to use Newton's first law to get through that. Alright, we're going to solve problems including horizontal and inclined plane. We're going to work frictionless and friction surfaces. We're going to look at vertical motion, rockets, scales, lifts, hoisting, two body systems, two masses joined by a string over a pulley. Those are all the examples that are in this section, so please make sure that you have a look at the entire video. I know it's going to be a while. I know it's a long video, but we'll get through it. It will be to your benefit, especially if you struggle with Newton's laws of motion calculations. All right, so let's have a look at the first thing, the relationship between mass and acceleration. So let's just have a look at these relationships so that we have a better understanding when we get into Newton's laws. If you have any misconceptions, it's best that you just pay attention. Alright, so take for example, if you have a moving van or moving truck and it's at this traffic light and the light turns green and the driver pulls away. Now at this point, when it's at the traffic light, it has stopped. Now, in order for it to move forward, right, so I want it to move forward, it has to accelerate. Now, the only way that that acceleration is going to happen is if we apply some sort of force. So we apply a force to the accelerator. Force to accelerator, and then the force in the engine causes the truck to accelerate and it moves forward. Now if I want to accelerate faster, I would have to increase the force, right? And if I increase the force, I'm going to end up with a faster acceleration. I'm going to leave much quicker. So what you need to start seeing here is there is a relationship between acceleration and force. And I can say that if I have if I increase the force, I'm going to end up increasing the acceleration. Essentially, if I look at the same kind of setup, except this time, my truck's sitting at the coming to the traffic light. So it's moving towards the traffic light. Now, in order to, when it gets here to the traffic light, it needs to stop. So now what the driver has to do is, it needs to slow down. And the only way to slow down is to apply a force to the brake. Right. So this is important. Right. So when we apply a force to the brake and we have a situation where it slows down, we can say that the truck, so here it was moving towards, that was its motion. Now you're applying the brake, it's going to slow down, and we can say that the truck is moving in the opposite direction of motion. Right, so now it's going in the opposite direction of motion, and the reason is because we have increased the friction. Right, more friction means more force opposing that motion, and that brings us to Newton 1. So now we can relate Newton 1 to Newton 2. So if he's moving towards this traffic light, and let's say he's far away, because he's far away, he can apply a small force on the brake. Right? If he's close and moving very fast and he needs to stop suddenly, we need to have a bigger force on the brake because we need him to stop much faster. So if he wants to stop suddenly, he must apply that bigger force, and there will be a greater negative acceleration. So he will stop much faster. So right now we can see that there is this relationship between force and acceleration, and we can say that a force can make an object accelerate. That much we do know. That's one conclusion. The second thing that we can say is that the acceleration is in the direction of the exerted force. I hope you guys are starting to see words that relate to Newton 2. Alright, so in terms of our relationship here, I hope you've seen the relationship. We can say the stronger the force, acting on an object, the greater the acceleration. Right? So I know that F net is directly proportional to acceleration. And if I have that kind of a setup, then the type of graph that I'm looking at is this. That is the graph of force and acceleration. I would recommend that you take this down, because essentially the types of graphs that we draw are always going to look like this, right? Force here at the bottom. Oops. I've got force here at the bottom in newtons and acceleration in meters per second squared. So that's the kind of graph, sorry, that should connect. That's the kind of graph that you would draw for the relationship between force and acceleration. Now, the other thing, let's move this up. Right, the other thing that can affect acceleration is mass, right? And so let's have a look at mass. So if I'm looking at the mass of these three vehicles, a school bus, a truck, a police car, in terms of mass, they're all different from each other. And let's say for the truck, for example, let's say it's a moving truck, and right, it's a moving truck, and it's moving its goods and it's full, so the mass is increased. Same for the school bus, it's full of children, so also mass increased, right? So let's say if he's at the traffic light, we know that he wouldn't be able to, there will be no quick acceleration. The reason for that is because it's too heavy when he pulls away from the traffic light. Also, when he applies brakes, let's say when he applies brakes for deceleration, that must be done in advance because it will take longer for it to stop. When we do momentum and we get into work, energy and power, you'll be able to see how these things actually affect the system. So from that, because I know of that mass and the effect it has, the conclusion I can draw is that the greater the mass, the smaller the acceleration. So that means that acceleration is inversely proportional to mass. And how we write that down is that A is directly proportional to the inverse of mass. So that's how you say it in words, and this is how we say it mathematically. So please make sure that you get your wording sorted out. I don't want to hear indirectly proportional, or that there's no mathematically there's no sign for inversely proportional, only for directly proportional. Essentially, if we're looking at mass, then I can also say that F net. So if I'm looking at bigger mass and I want to accelerate, if I do want to do a quick acceleration, I've got to use that bigger force, right? So when we're looking at, and I said this before, F net is directly proportional also to the mass, because if the mass increases, my force must also increase. So that's F net directly proportional to mass. So for the other one, for the acceleration, the graph that we'll use for that one looks like this. All right, so this is the, this is the inversely proportional graph. Now we don't like inversely proportional graphs because of this relationship here. It says it's directly proportional to the inverse of mass. So if, for example, I was given a table and it was a mass versus acceleration type of table, Then let's say they gave me, I don't know, 1,000 here, then 2,500, then 3,000, then 10,000. And here they said the acceleration was maybe 2 meters per second. Oops. Let's say it was 28 meters per second. Then over here it was 22 meters per second. Then it was 16 meters per second. Then all of a sudden it was 7 meters per second. When we plot this graph, we cannot plot these values as they are. So your mass values will have to be 1 divided by mass. So for each value, for the first one, for example, I'll have to plot the mass at 0.001. Then for the second one, I'd have to plot it at 0.0004 and so on. Right? So please make sure that when you plot this graph, the inverse graph, it should give you that. Except here, you'd have mass. And over here, here you'd have your variables at 1 over mass. And over here, you'd have acceleration. So please make sure that when you're working with these graphs, you make sure that you sort things out. And let's get into Newton's second. All right, when we're looking at Newton's second law, we're looking at when a force, an F net force, is applied to an object with a mass, it will accelerate in the direction of the net force. And we discovered that we have acceleration is directly proportional to the F net and inversely proportional to the mass. So if I consider two balls, one is 1 kilogram and the other one is 10 kilograms, let's say ping pong, not a ping pong ball. Let's say I have a ping pong ball versus a bowling ball. Which will experience a greater change in motion or move away faster if kicked with the same force? Then you need to understand it's the smaller one. So if I have a change in velocity, then I would have acceleration. I would have acceleration. So I know that my formula of acceleration, and if you watch those videos on kinematics, is VF minus VI all over T. Alright, so I know that, let's have a look at these 3 or 4 situations. Let's say I have velocity is 0 meters per second. So if something's at rest and I apply a force, then I'm going to have velocity increases and I'm going to get acceleration. So I'm going to get a positive value for acceleration. Let's say I'm moving, which means my velocity is greater than 0, and I add a force to that, then again, my velocity will increase, and I'm going to get acceleration. So again, a positive value for acceleration. The third scenario, let's say I'm moving. Again, my velocity is greater than 0. Plus I add a force in the opposite direction of motion. Then I'm going to have my velocity decreased. Oops. And that's going to end up with an acceleration again, which will be a negative value. So essentially, as we're working through this, and I look at something like F net, or the net force, or the resultant force, essentially, I can say that F net is equal to the forwards minus the backwards, which means in any of these situations you must choose a positive direction. You must indicate to your marker what that positive direction is, and what's actually happening is your F net forces are all the forces that act on your object. So you could have all your forces in the X direction, your forces in your Y direction. You could have a normal force. You could have gravity, or Fg rather, right? All of these forces put together, in addition and subtraction, will give you a net force, which is the sum of all forces, and you must account for the sum. So this base formula here is not an official formula, but it's a formula for you to manage all of your forces. Some people like to do it all together, other people like to separate things. So it's up to you really how you want to sort your forces out, but that's a general idea. So from grade 10, right, how do we work out these forces? So there are things like acceleration, velocity, displacement. All of those things play in here. So I need to make sure that when I use, or when I do Newton's laws, equations, or calculations, problem solving, I make sure that I go back to my grade 10 stuff and I can use equations of motion. So I'm allowed to test equations of motion in Newton's laws calculations. So these four formulas, you have to know them, right? They play an important role in doing calculations. You may use any of these formulas to do any of your problem solving, right? And then Newton's second law comes up with its own formula, right? Newton second law formula, right? It says, the net force is equal to the mass multiplied by the acceleration. So I've got F net is equal to ma. Your F net is a resultant force. Now that means that you need to first find F net before you substitute that value in here. So having just an applied force is not enough. You need to look at all the forces acting on your object in order to put anything into this formula. Your mass will be done in kilograms. So if they give it to you in grams, please make sure you the necessary conversions and so on. Acceleration, I should just do that to show you that, will be in meters per second squared. Please remember that both force and acceleration are vectors, which means all their answers require a direction. If you don't have a direction with your answer, they're inclined to not mark your question. So please, let's start building good practices. And for manipulation purposes, you can use this triangle. But your base formula is F is equal to MA. Alright, so all we know about this formula, or what we do know about this formula, is that acceleration is the product when force acts on a mass. We know that the greater the mass of the object being accelerated, the greater amount of force needed to accelerate that object. And we know that heavier objects need or require more force to move them. So those are the little summary points that we're going to look at. All right, the next thing that we're going to focus on is problem solving. Right, I'm inclined to remind you about the slide that we did at the beginning of the year with problem solving. Develop a logical system when you're in class. Good work becomes a habit. All right, so here's how we sort through some of this stuff. Right, the first thing you need to do is identify what's given to you and write them out using the correct SI unit. Don't forget you do have a data sheet. Use it to the best of your ability and don't do any guessing. After you write down information that you have, you need to look at what they're asking you for. Identify your formula, right? If you struggle with math, then I would suggest that you manipulate the formula before substitution. But please make sure that the formula, your base formula, that must come from the data sheet. So please don't manipulate before that. You won't be getting any marks for that. Another thing that I could say is important, once you've got your formula, the next thing that you should do is draw a diagram, especially free body diagrams. Right? Draw a diagram so that you can see exactly what is going on, and you're going to see in these next examples. I'm going to go through quite a bit of free body diagrams. After you're done, you substitute, write the problem out carefully. Don't forget the SI units. In this section, what's very important, please make sure that you have direction. I don't want to see things like you using words for SI units. For example, if you're working out time, it's in 10 seconds, please. You cannot have time is equal to 10 seconds. That is not an SI unit. That will be marked as incorrect. So please make sure you use the correct SI units. You put in your directions for all vector quantities. I'm going to go through a few examples now. Please make sure that if you're going through these examples, if you feel like you're confident, write down the example, draw the image that accompanies that example, do the calculations and see if you did it right. If you're not confident, watch, pay attention, take as much notes as possible. What I say is just as important as what you're seeing on the screen. So take down that information so that it can be beneficial to you. Right? But please try and work through these so that you can have a better understanding. So I'm not going to be doing basic F is equal to MA calculations or examples. I'm going to go straight into the system problem solving. And then from there we can move forward. If you do need help with basic stuff, then please send me a message and then you and I can have a discussion about that. All right, let's have a look at example 1. All right, in example 1, you've got a force accelerating two blocks or masses and there's no friction. So I'm just going to add information. You obviously add information to yours. So in this situation, we've got a pushing force of 12 newtons. You've got mass 1 over here at 2 kilograms and mass 2 here at 4 kilograms. Right, they tell you that there's no friction, so your value of mu is equal to 0. What they want here is the acceleration, and they want the net force on each of the blocks. So when I have a look at something like this, what you need to recognize is when things are attached to each other in any way, this whole thing, right, becomes one system, right? So because they attach to each other, and they are one system, we can do all of the calculations together. So the first thing they want to know is about acceleration. Now, if we say they attach together, the first thing you need to do is sort out the mass. In terms of mass, I need a total mass. So mass total would be 2 kilograms plus, jump the gun there. Mass 1 plus mass 2 is 2 kilograms plus 4 kilograms, which gives me a total mass of 6 kilograms. So when I'm doing my calculations, I don't have to do multiple calculations unless they ask me for that. So if I'm looking at question A, please make sure you get these diagrams into your books, information into your book, so that you know what's going on. When I look at A, I know that I have a force. Let's see. One singular force. So I can call it F net of 12 newtons. And I've got a total mass of 6 kilograms. And they want from me acceleration. Right, so because the information is quite basic, I can say that acceleration, what am I doing? Identify my formula. F net is equal to ma. I can manipulate and say A is equal to F over M total. And I've got 12 divided by 6. My final answer is 2 meters per second squared in the direction of motion. Right? I must mention that. Right? And there's my first answer. So 1, 2, 3, 4. That is the acceleration of each block. It's also the acceleration of the system. Because they're touching one another, I can put it under a blanket calculation. Right? B. They want the net force on each block. Right? So now you can separate it. So we use this acceleration that we found and we apply it for each one. So I'll say mass 1 and I'll say F net, and look at my notation, 2 kilograms is equal to MA, and for mass 2 I say F net is equal to 4 kilograms is equal to MA. And all I'm going to do is substitute, and I'm going to get 2 times 2, and over here I'm going to get 4 newtons in the direction of motion, and over here I'm going to get 4 times 2, which is 8 newtons in the direction of motion. And there's my answers for B. So look at how I've laid it out. Look at my notations. Work in a systematic way. 1, 2, 3, 4, 5, 6. 6-mark question. Right? It's easy marks. Know how to do basic calculations like this. Right, let's have a look at the next example. And the second example looks at forces accelerating 3 masses, and this time it has friction. So let's look at some of the information that I can add to this diagram. Alright, they're going to give me here 120 newtons of an applied force, which is a push. I've got 3 masses. Mass 1, is 2 kilograms, mass 2 is 1 kilogram, and mass 3 is 3 kilograms. They've given you a mu value here, so you know you have some sort of friction. And they're asking three things. What is the force of friction? What is the acceleration? And the net force on each block. So when you get into these calculations, the first thing, like I said to you, because they're touching one another, they have one system. Right? They can function as one object in total. Oops. So in terms of mass, what I could do is I just say mass total is 1 plus 2 plus 3, and I've got 6 kilograms. So the mass done. Now when I'm looking at this one system, what I can do is I draw myself a little free body diagram. It's on a surface, so I've got force of the normal, and it has mass, so I know I've got Fg, or I've got weight. I know there's an applied force in this direction, so I've got force applied, and I've got force of friction here. So now in terms of my values, for weight, I've got 6 kilograms, and 6 times 9.8 is going to give me a total of 58.8 newtons. And my F normal is also 58.8 newtons in the opposite direction. My force applied, they've given us at 120 newtons. And I don't know force of friction, but I do know that the mu value is 0.5. So I've written down all of my information. From there, I can start doing my calculations. And the first calculation they want you to do is what is the force of friction. Now I know that there is motion, and that's kinetic energy, so I'm going to use force of friction of kinetic energy. The formula is Fk is equal to mu k times Fn. I know my mu value at 0.5, multiply that by 58.8, and my force of friction, that's half, is 29.4 newtons in the direction, opposite direction of motion. Because it is friction, that value should always be a positive value, and it's going to give you an opposite direction. Right, with B, they want the acceleration. Now I know for acceleration, F net is equal to ma. And this F net here is a resultant force. And I can see that I've got a force going in the opposite direction of motion, which is 29.4 newtons. And I've got a force applied. So what I can do is I can do this in two ways. I can say that F net is equal to ma, and F net minus the force of kinetic friction is equal to ma. Or I can say that F net is equal to ma, and I could have said F net is equal to forward minus my backward. And my forward force here was 120 minus my backward force, which was 29.4. And I get a total here of 90.6 newtons. So I can say 90.6 is equal to the total mass, which is 6 kilograms times acceleration, giving me 90.6 divided by 6. And acceleration is equal to 15.1 meters per second squared in the direction of motion. Or here I could have just said F net, which is 120 minus 29.4 is equal to 6 times A. I would have still got 90.6, which is equal to 6A. And I would have still gotten an acceleration of 15.1 meters per second squared in the direction of motion. So it is up to you how you're going to sort that F net out. Just make sure that you sort out the F net before you substitute it into this formula. And then that leaves us with C. C says, what is the net force on each block? Right, the net force on each block, you'll have to do each one separately, M1, M2, M3. You'll have force of the 2 kilograms is equal to MA. Force of the 1 kilogram is equal to MA. And force of the 3 kilogram is equal to MA. And all you do is you incorporate those values in direction of motion into your calculations. This was 1 times 15.1. You get 15.1 newtons in the direction of motion. And the last one is 3 times 15.1. And that gives you 45.3 newtons in the direction of motion. So what we need to make sure we take from this example is that if they're touching one another in any way, they're one system. If they're one system, it means we can have a total mass. And that means that all masses experience the same acceleration. Free body diagram, sort out the information you have, sort out the information that you want, working out kinetic friction, sorting out F net. There's method 1 here and method 2 there. Up to you how you want to sort that out. And then when we come back here, remember acceleration is the same for all masses. And you would have also noticed the other thing. Please make sure that you put, and look, I'm not lazy, and make sure that my directions at the end of every single vector type of calculation. And let's have a look at the next example. Example 3, finding the coefficient of friction. We have a toddler dragging his wagon of toys, and he pulls with a force of 16 newtons at an angle theta to the horizontal. The weight of the wagon is 49 newtons. Calculate the value of the coefficient of friction that will stop the wagon from moving. Right, when we have an example like this or a situation like this, best to get some sort of diagram that can make sense of what's going on. Right, so when we look at our little setup here, we need to sort out our information. So I know that, I'm just gonna move up a bit here and just work underneath here. You can have a look at my diagram. Right, I know here that the toddler is pulling with F1 here, which is 16 newtons. So that's sorted out. It says a theta to the horizontal. Now, if I look here at this little boy, they gave you this angle here at 60. But when they talk about theta, theta must always be from the horizontal upwards. If I'm looking at the Cartesian plane, my angles go from east. It goes anti-clockwise. So when I measure theta here, the angle theta would be 30 degrees, because this technically makes a 90-degree angle there. So that's 30. The weight of the wagon is 49 newtons. Put that in. It says calculate the value of the coefficient of friction. So I know there's a friction here. But But at this point, I don't know what that force of friction is. So we'll get to that. Right. Our biggest problem here for these types of questions, or the biggest problem we have right now, is that if there's an angle, right, we need to take that angle into consideration. So essentially, if a force is parallel, if a force is parallel to the earth, then we can use that force for what it is. But if the force is at an angle to the earth, then that force is actually F rays. And if they give you F rays like that at an angle, we need components. So technically, this boy is doing two things. One is that because of that angle, he's got a lifting force. So I've got Fy. But he's also pulling this thing forward. So I've got a pulling force of Fx. So that's the information that I have right now. You need to see that where that theta goes. And he's pulling with a force that is not parallel to the earth. So we need those components. So let's sort out those components. So far this 16 here is F net, but at an angle. So I can't use that value. I need to sort out my components. So I've got F of x is equal to F cos theta, and I've got F of y, which is equal to F cos, F sine theta, right? If I'm looking at F cos theta, I've got 16 cos 30 degrees, and that's going to give me 13.856 newtons. All right, with the Fy, I've got 16 sine 30, and that gives me 8 newtons. All right, for now, I'm just using these values, so I'm not going to round off, not going to write directions, nothing. Now, essentially, I need to account for what's going on with my object. I know that I've got Fg here, and they gave you that at 49 newtons. I also know that going upwards, I've got F sine theta, and that is at 8 newtons. I know that my wagon is being pulled, and that's at F cos theta at 13.856 newtons. But I also know that I have a frictional force. Force of friction. Right. Now, I know that my force, my normal force, can't be equal to, so if I look here at my normal force, I still have my normal force. I have two forces going in the upward direction. It cannot be equal to 49 because here I've also got a lifting force. A force that is technically aiding my force of my normal. Because my two forces are acting in the same direction, I have to say that Fn, my force of my normal, which is equal to 49 newtons, minus Fy. Because they're in the same direction, they aid each other. So it's not the same as Fg. So Fn is equal to 49 minus 8, which will give me 41 newtons. And that's my force of the normal perpendicular to the surface. Right? Have a look. It's less than the force of the normal, because now it doesn't have to compensate for all of that. If it's just sitting there, all of that gravity, it can be less because it has assistance from the force in the y direction. So this is what my free body diagram, please make sure you use a ruler when you do yours. That's what my free body diagram looks like for this kind of setup. Now, if I'm looking at the question, it says, calculate the value of the coefficient of friction that will stop the wagon from moving. So right now, the force, let's use another color so I have a better idea of what we're doing. The force in the x direction moves the block forward, right? We're not talking about lifting. So therefore, the maximum friction to stop it must be equal to Fx. I don't want this block to move. Fx causes the block to move forward. So right now, my force of friction must be greater than my force in the opposite, in the forward direction, in the x direction. Because this thing takes the object forwards. Force of friction is going to take it backwards. If the force of friction is greater than the forward force, then the block would not move. So now, once my equation is set up here, that's how I'm going to sort it out. I know force of friction is mu k times Fn. And my force in the x direction I worked out is 13.856. That's why I didn't round off. Now they want you to find the coefficient. So we're looking for mu k. So now we've got mu k times Fn. And we worked out Fn. Here's Fn here. At 41 newtons. Multiplied by 41 is equal to 13.856. I need the mu k by itself. Divide both sides by 41. And mu k must be greater than or equal to 0.033795 and I can round it off because that's my final answer. Must be greater than or equal to 0.34. And there's my final answer. So that tells me that if the mu value is greater than or equal to 0.34, then the wagon will not move. Alright, so when we're looking at an example like this, please make sure that if anything ever moves at an angle, you need x components and y components. Y components are always going to move the object up, so we get a lifting force, and x components will move it forward or backwards or whatever the case is. Make sure you draw out a free body diagram, because a free body diagram would show you that I had more than one force going upwards, which means that my normal force was being assisted by a lifting force, because now it doesn't have to do all of the work against gravity. Something's aiding it, so that the normal force is decreased. So when you have angle problem solving to do, you can't use the normal force. Make sure you decrease that value, If you don't decrease the value, you're going to see that you have a problem. If they want the block to not move, then friction must be greater than, I can write this down here. For something to stop or to have no movement, right? The force of friction must be either greater than or equal to the applied force. That you must remember. And then you set up your equation just like how you do inequalities and equations in math. Don't take any shortcuts. Look at the sign and make sure that I keep my sign the same all the way. I don't change it at the end to equals to all of a sudden. Make sure you follow your mathematical rules. And look, I'm working in a logical manner. A little bit untidy, but you need to make sure that your marker can see exactly what's going on in these types of situations. All right, let's have a look at the next example. Example 4, tension forces. It says calculate the tension force in T1 and T2 if two blocks joined by a string are moved across the floor by a 100 Newton force. Right, so let's get some information on. Right, the first thing is you've got two masses. This mass is 14 kilograms, and the mass next to it, that is 6 kilograms. They're telling you that you have an applied force here of 100 newtons, and they want to know the tension force for T1 over here and T2 over there. Alright, so when I'm looking at something like this, and I want to draw that free body diagram so that this whole thing makes sense, I've got my first mass over here. My second mass is not far off. And what's actually happening is my first mass has an applied force that's doing that. So force, alright. And my second mass is being joined to that first mass. So that's the first thing. The second thing is both of my objects have mass and are on a surface. So I'll have my force of gravity and I'll have my force of the normal. So let's get that all sorted out. I have Fn of 1 and I have Fn of 2. I've got M1G, M2G. I've got F applied here. And that's what I'm looking at. So, in terms of my information, I know that this is going to equal 100 newtons. I know that M2G is going to be 6 times 9.8, which is 58.8 newtons. And M1G is 14 times 9.8, which is 137.2 newtons. Alright, that's what I've got here. And over here, don't forget to put that in as T, force of tension 2, right? And force of tension 1. I also know, and I told you guys this previously, if two objects are touching each other, these are touching each other because they're joined together by a string. I've got here one system, so I can work out the total mass, 14 plus 6, and that's going to give me 20 kilograms. And I can use that information when I'm doing my calculation. Alright, so the first thing that I have to look at is, in order to get tension, right? In order to get that tension, I'm looking for force. Now, let's look at these relationships. Sorry about that. This force here, this force applied of 100 newtons, this thing accelerates the system. So now I have an F net that moves this whole system. I also have the mass of the system. So the first thing I can do is, I can say F net is equal to MA. The F net we have here is 100. The mass is 20. 100 divided by 20. A is equal to 5 meters per second squared in the direction of motion. So now I have the acceleration of each mass has the same acceleration. Alright, now they want T1 and T2. Now remember, I need acceleration because I need force. Now if I look at T1, T1 acts directly on this first mass over here at 100 newtons. So technically for T1, I can say that therefore T1 is equal to 100 newtons because M2 is attached directly to the applied force. Is it M2 or M1? Yeah, M2. Right, so that's sorted out. So that's T1. Right, T2 is attached by a string to M2. So what I'm actually looking at, if I have the setup here and I have M1 there, that's its force of tension. So it involves that M2. So when I'm looking at it now, it's not this type of tension here in that second bit is not, it shouldn't be as much as 100 newtons because it's being pulled by another block. So if I look at that and I say F net is equal to M2A, M1A, then I can say that M1 is 14 kilograms multiplied by the acceleration. 14 times 5 is 70 newtons. And that makes sense because it's not the same. It shouldn't be the same. It should be less than that. Right? It has to be less. So then I can say therefore T2 is equal to 70 newtons in the direction of motion. Don't forget here, in the direction of motion. Sorry about my handwriting, but go with what I'm saying. It will make better sense. Right? What I could also do, if I wanted, let's say I panicked, I could say that T2 is equal to M2, M1, all over M total times the force applied. It's another way of looking at it, another method. So I could take M1, which is 14, divide that by 20, multiply that by 100. That just worked out like that. And I also end up with 70 newtons in the direction of motion. Right. So M1 is a part of the M total, right? But if I multiply it by the force applied, it can still give me that value of the T2. So therefore T2 is equal to 70 newtons, and that's your final answer. Right, the next thing we're gonna, and then they can give you options where you have like a surface, and they give you 3 masses, 4 masses, situations like that. Same thing. Work with the system, right? Allocate, let's say T1, T2, T3, whatever the case is. Get your system together, get the acceleration of the entire system, and then you can work out the tension of each one. So let me put this down properly for you. If I wanted the tension, this is a formula that is acceptable but will not be on your formula sheet. So tension on a horizontal surface, right? We can say the tension on the block is equal to the mass of the block all over the total mass of the system multiplied by the applied force. And that's how you work out tension. And remember, when you have these types of questions, there's no pushing. It's always going to be something being pulled. It has to be pulled because you need the string must be taut in order to get that tension force. Right, so pushing a block is not going to give you this, but this is another sideline formula that you can use to get to your answer. Right, I have to do 2 pulley systems. Let's get to that. Example 5, we have a pulley with 2 masses on a horizontal surface and there's no friction. It says a 15 kilogram box rests on a frictionless horizontal surface. Let's get that information on. It's 15 kilograms on a frictionless, so mu is equal to 0, horizontal surface attached to a 5 kilogram block which hangs over a massless frictionless pulley. What is the acceleration of the 2 boxes? And what is the tension in the rope? And we'll say that this is T1 and T2. Alright. When I have a situation like this, like I said to you guys, I say this every time, draw your free body diagram so that you can see what is going on. So I have a mass over here, and this mass is being pulled this way, and when it gets pulled that way, oops, do that, it goes down some sort of system. So get that right. Goes down this way. Oops. Yeah. Let's do that. Okay. Sorry, I just saw this out. Right, I've got a mass, the first mass that's doing this, and I've got force of tension 1. Now that force, or that object, the 15 kilogram object, is sitting on a surface and it has mass. So if it's sitting on a surface, it has a force of the normal and it has a force of gravity. So I have Fn, and here I have Fg, or rather M1G. On the other side, I've got my little pulley over here, and coming over the pulley, I have my other mass here, and that's going towards the earth, so that's M2G. It's not on a surface, but it is attached to a string, And that's doing that, and I've got FT2, that's FT1. So this is what my free body diagram looks like. Now, how you work through these types of examples is that you've got to make certain decisions. The first thing that I want you to note, just going to use this color, is you would notice that these two objects are attached to each other by this string over here. So I know that I again have one system, and that system has a total mass of 15 plus 5, which gives me 20 kilograms as my total mass. Right? The next thing that you need to do is, once you sort out that situation, you need to choose a positive direction for acceleration. Right, so now I'm going to say, and I usually use this idea here, is if there is this pulley over here on a massless, frictionless surface, that means because the pulley is frictionless, right, the direction of the system, right, will be, how do we say, affected by the mass over the pulley, right? That means that this whole system is going to move, like this. So what we mean by we must choose a positive direction, I draw something like this, and I show you the positive direction of my system, and I say that that is the positive acceleration. So that's mass 1 and that's mass 2. So what I've got to do now is I've got to say, if mass 1 moves to the right, then it would be considered as a positive movement. But if mass 2 moves downwards, then that's considered positive. So this mass needs to move to the right, have a look there, and this second mass needs to move down, and that's sorted out. So once that's done, you've got your directions. The next thing is you need to look at what force is going to drive this thing. So like I said, the mass that's over the pulley is the driving force of the system. It's the thing that makes the system move. So I know that my force, or my FG, that's going to bring this move, wait, just another color. The force that's driving this is a force that brings this mass down, and that is M2G, the force of gravity. So when I'm working this out, I will say Fg is equal to M2G, mass 2 is 5 times 9.8, and that should give you 49 newtons in the direction of motion. And I can just note here that this mass is pulling M1. So it is the force applied to the system. So now I've got force applied, and I've got total mass up here. So therefore, that allows me to calculate the acceleration. So I can answer A, which is F net is equal to MA, where F net is 49, because that's my driving force here, is equal to 20 times acceleration. And I'm left then with an acceleration of 2.45 meters per second squared in the direction of motion. So this means that M1 accelerates at 2.45 meters per second squared to the right, and M2 accelerates at 2.45 meters per second squared down. So that's the first thing that you need to sort out. There's question 1 done. Right, the second thing they want to talk about is they want to talk about tension. Now let's just have a look here at our little system. If I'm looking at tension, I need to understand that the string that both of these masses are attached to is the same string. So if I look at previous examples, if the two masses are joined by a string, it means they're one system. So if I have a look here, here's my string here. There we go. One string. And one string tells me that technically, this is question B, T1 is equal to T2, and you can make a note here, they share the same string. That's why the tension is going to be the same. Now you have two situations. Mass 1 looks like this at the moment. And mass 2 looks like this. Now when you have these two and they share this, it's the same. When you do these kinds of calculations, work with the mass that has the least amount of forces. Oops. Right? This is if we're working out tension. So if I'm looking at these situations here, I know if I look here at mass 1, I know that my force of my normal and my force of my mg are not relevant because my object is not moving up or down. So they don't really matter right now. M2G, or M2 rather, it has an upward force and it has a downward force. But M1 has only FT1, which is moving to the right. So the one with the least amount of forces is M1. So all I'm going to do is I'm going to say force of tension is equal to mass times acceleration, and that's going to be 15 multiplied by 2.45, and that's going to give me 36.75 newtons to the right, and that's the value for T1, right? And I know that T1 is actually equal to T2, which is equal to 36.75 newtons. Now, if you're unsure about what I've just done, let's just have a look here. Let's say I used M2. So here we used M1. Say I used M2. right? The first thing I need to figure out, I know that going down, remember what I said, is 49 newtons, but going up, I don't know. So I'm going to say Ft is equal to mass times acceleration, which is 5 times 2.45, and that's going to give you 12.25 newtons upwards, right? Now I've got two opposing forces, and remember what I said about F net. F net is going to be equals to forwards minus backwards. And my forward force here is 49, and my backwards force is 12.25, and that should give me 36.75 newtons, and that is T2. And look, those values match. But can you see that when I used M1, look how basic my calculation was, because there was only one force. But M2, look how intense the calculation is, because you had a force going down, you had a force going up, they oppose each other. You had to first calculate, you had to then, after you calculate the force, your upward force, you still needed to work out what that tension actually was. So remember, your forward force is pulling this whole system down. It creates quite a bit of tension, but your backward force is pulling it up a little bit, so it counteracts that, and then that value should be less than that sort of setup. Alright, the next thing I'm going to show you is the same type of system or the same setup, except this time I'm going to add in friction, and I'm going to show you some cheat ways of how you can find the tension using other formulas or other methods and so on. Example 6. We've got a 12 kilogram box rests on a horizontal surface that has a coefficient of kinetic friction, so we know it's moving, of 0.25. The 12 kilogram box is attached to an 8 kilogram box with a massless massless rope over a frictionless pulley. They want the acceleration of the system, and they want the tension in the rope, T1 and T2. So the first thing that I'm going to do is I'm going to set up my free body diagram, and I've got this mass here. Oops, let's undo that. I've got a mass here, the 12 kilogram box. I know that it's moving in that direction because it's on a surface. I also know that it has the force of the normal, and it also has a force of gravity. So that's that, F of the normal, and then M1G. Also, I've got force of tension 1, and that whole thing's over a pulley, and that pulley holds a second mass over there, and that second mass is experiencing a force of gravity downwards, and that's M2G, and it's got an upward force of tension FT2. So that's my free body diagram of my system. They've also told me that my mu value here is 0.25, so I know that essentially in this whole diagram, on my surface there's a force of friction going in the opposite direction of motion, right? And so I have force of friction there. So there's an added bit of information. But like I said, we're going to look at this whole thing the same way, except now we've got forces in the opposite direction of motion. So the first thing here that I need to recognize is I need to choose my positive direction of acceleration. So I'm going to say acceleration would be positive if my system does this. So I make the marker aware of what I'm doing. And the reason for that is, now that I know that, is because my M2G, which is 8 times 9.8, and that's 78.4 newtons, is the driving force of this whole system. It's going to cause my 12 kilogram mass to go over the pulley system. And because they're attached by a string, I can also say mass total is equal to 12 plus 8, and that gives me 20 kilograms. Right. The only problem now is that I've got something that's opposing this. M2G is my forward situation, and my force of friction here is what's holding it back from going over. So the first thing that I need to do is I need to find the acceleration of my system, right? So when I'm doing my calculation, I need to make sure that I'm looking at F net or whatever the case is. So I know that F net is equal to the forward minus the backward, and my forward is M2G minus the backward is the force of friction. Now M2G I've worked out there is 78.2 newtons minus force of friction. Now my force of friction, what I must understand about force of friction is it has its own formula. I know that I'm using kinetic friction, so I've got mu k times Fn. Put that in brackets. Now my M1G is 12 times 9.8, and that's going to give me 117.6 newtons. And I know that my force of my normal is also 117.6 newtons. So I've got my force of the normal, check, and I've got my mu value. So I'm going to say 78.2 minus 0.25 multiplied by 117.6, and that's going to give me 78.2 minus 29.4, and then I'm going to end up with 49 newtons, which is my F net. And I can use that F net to answer question 1, which is the acceleration. So now I'm going to say F net is equal to MA. My F net is 49. My mass is 20. With my acceleration, get acceleration by itself, and the acceleration is 2.45 meters per second. Right. So once I've got all of that information, I now have acceleration. So I'm in a position where I can answer my next question. So the next question you have is they want the tension in the rope. Now, from the previous question, we know that tension, right, is caused by mass and acceleration. Okay, so now we've got to look at our two systems over here. If I have a look, I've got my M1, which has Fn, M1G, Ft, and F force of friction. I know that those don't count, and I've got my M2 here, and that's got M2G and if I'm going upwards, Ft. So if I look at both of them, right, and remember my tension is giving me my force applied at the end of the day. And I also know that T1 is equal to T2 because they share that string. Now, initially we said that we'll use the value that the mass that has the least amount of forces, but essentially speaking, we can sort that whole situation out quite easily. So let's look at M1. If I use M1 for my calculation, I need to understand what's actually happening here. When I'm looking at the position of mass 1 is sitting on this, mass 1 is sitting on the surface. Now this whole system wants to do that. But if I look at Newton 1, if my mass is sitting here on the surface, mass 1, it has no tendency to move anywhere because it has mass. So it's actually, yes, it's being pulled over this pulley, but it's also resisting. And what's aiding its resistance and helping it to resist is the force of friction. So if I look at M1, mass 1, and I want that tension, then I can say F is equal to MA, right, plus my force of friction. Because both my tension force and my force of friction are both resisting to go over this pulley. So I can just say 12 times 2.45 plus the force of friction, which was 29.4, and that's going to give me 58.8 newtons. And that's the value of T1. Right? So remember, you have the force of the mass, right, added to the friction. And the reason for that is they both are being pulled down, but because of inertia, the mass doesn't want to go anyway. And because of the coefficient, let's say, because of the mu value, friction's assisting that inertia to not let that happen. Now I can do a check because I know that T1 is also equal to T2. So let's say I did a calculation for T2 separately. If I look at mass 2, I've got a force that's bringing this whole mass down, which is M2G. That's going down. And I said that was going to be 8 times 9.8, and we ended up with 78.4. Right? Now, that's the one force that's pulling it down. What's also happening is there's something that's pulling it up as well. So F is equal to MA, and I know my mass is 8 times 2.45, and that gives me 19.6 newtons. And that's pulling this whole thing up, and this is going down. Now to get F net, we know I must take forward minus backwards. And I'm going to take 78.4 minus 19.6, and I should end up with 58.8 newtons, essentially, which is T2, which is also T1. So if you look at my two answers here, they should be the same, regardless of what you've done. Now this tension thing can become a little bit confusing, especially when we have systems like this. So I'm going to give you a cheat way or a method that you can use that will guarantee you that you get through these, especially this whole idea of inertia coming into Newton's second law. Remember, you need to know how to integrate the two. So let's have a look here. If I have tension, right, and I said to you guys now that tension is caused by mass and acceleration. So if I have force of tension, it can also be referred to the applied force. Now let's say I had a table here, and over this table I had this system, and in this system I had this, a rope. Sorry. I had a rope coming over here and doing that. On top of my horizontal surface here, I'm going to have mass 1 and T1, and then T2, and hanging off the edge here, mass 2. So that's the setup. Alright, so let's just break this down quickly. If I'm looking at T2, alright, so let's do the calculation for T2. T2, the mass is accelerating downwards, right? So I'm looking at that situation, okay? It's going down. The tension should be less than that force, the driving force that's pulling it down, right? Because gravity would suggest, if I had gravity, things easily move downwards. So I have my tension here, which is going down, right? Tension going down, and my mass is also going down. So they're assisting each other. So if I wanted to work out T2, I'd say T2 for a downward motion is equal to M2G minus M2A. It's not a formula that's on your formula sheet, so you must memorize it, sorry. So tension is equal to the weight minus the force of gravity. Or rather, let's say force of gravity, force applied, which is your driving force, the thing that's bringing it down, right? Now, let's say in the same situation, let's say the system was moving in this direction, okay? And now they ask you for T2. Notice here that T2, if the mass accelerates upwards, there will be more tension. Just going to reduce this. More tension. The reason for that is gravity is downwards, but your force is now going in an upward motion. So it's going against gravity. So because of that, you have a pulling force against gravity. And that's a problem. So how we work out that, we would say is T2, if it's moving upwards, is equal to M2G plus M2A. Right? Those are your two little formulas that you're going to need to memorize and know if you are working out in any circumstance T2 for a pulley system like this. If I were looking at, just change this color. Sorry. Okay. If I were looking at the same setup, but then this time I'm looking at T1. So now I'm working over here. Okay. If I'm looking at T1, right, T1 is technically the force applied that's pulling T1, right? So if the object accelerates, right, that way, right, if the object accelerates across to the right, then T1 is technically equal to MA, which is F is equal to MA, right? Nice and basic. But if there is friction, in the presence of friction, that situation changes a little bit. Like I said to you, you've got a mass, which means it has inertia, and it will resist movement, right? Aiding that is friction, which also opposes motion, right? So they function together. So if I wanted T1 in the presence of friction, it will be T1 is equal to MA, rather M1A plus the force of friction. And that will give me the value for T1 in both situations, right? One with friction, so that's for no friction, and one for if there is friction. So these are cheat formulas that you can memorize and get thinking about, so that you have the ability to work through these types of questions with much ease, rather than being in a situation where you're trying to figuring out, is it worth, is it not. It's just a faster way of memorizing things. Right, so this is the end of this video for Newton's second law. I'm going to upload a second video after this on inclined planes, and that's going to look we're going to do all those ones with inclines and pulleys and so on. But yeah, you can, after you're done here, you can go to the next video and then start there, and then we'll do activities or whatever the case is.